The Joe Rogan Experience.
You've done an amazing job in this book of trying to boil it down for dummies like me, but it's hard. It is a complicated and insanely nuanced subject.
Yeah.
And it's one of those things where it like this many worlds theory, for one example, the just the possibility that there's like explain that.
Sure.
Explain for people that don't understand what quantum mechanics even means. Give them just like a little bit of that, and then explain many worlds theory.
Yeah, good. This is what I'm here to do. So,
Thank you.
An electron, take an electron. Quantum mechanics should apply to the entire universe, but it becomes unmistakable when you look at little tiny things, right? So we always are talking about electrons or atoms and so forth. An electron has a position, and, well, sorry, let me not even say that. Even that was wrong. It's just so hard to correctly talk about quantum mechanics, right? If you were Isaac Newton, before there was quantum mechanics, there was classical mechanics. And basically, quantum mechanics and classical mechanics are the only two big frameworks that have ever existed in physics. Classical mechanics was so good that everyone thought that was just right, and it was all a matter of filling the details until quantum mechanics came along and changed things. In classical mechanics, an electron is a point. It has a position, a location in space, and it has a velocity. It's moving somewhere. And from that, you can predict what's going to happen. Okay? Quantum mechanics says, no. The electron has a wave function. So if there's a wave, sometimes you hear this debate about are things like electrons and photons particles or waves. The answer is that they are waves. And the wave function has this weird property that when you're not looking at it, it's a wave, it's all spread out, or it's localized somewhere, but it obeys an equation, the Schrodinger equation. So far, so good, just like regular physics. There's a thing, the wave function, it obeys an equation, the Schrodinger equation. You can predict what's going to happen next. But the weird thing about quantum mechanics is that there's a whole separate set of rules for what happens when you look at the thing, when you observe it, when you measure it.
That's where things get squirrely with people describing it, right?
Yes.
And that's where they want to go woo-woo on you.
It's an opening to be woo-woo, right? When you say, what do you mean observe something? Like, does it have to be a conscious being? Can it be a video camera? That's just weird, right?
Is it the act of measuring that changes things?
Well, this is the puzzle, okay? This is what is called the measurement problem of quantum mechanics. That the rules we teach our students at Caltech or anywhere else when we teach them quantum mechanics in their sophomore year of college, the rules say when a system is observed, when it is measured, its state, its wave function, changes dramatically, suddenly, and unpredictably.
Now, let me ask you this. How do we know this based on if you're measuring it and it changes? How do we know? Because we didn't measure it before. Like, what observations are we making that we understand the state of it before it's measured without measuring it?
Good. There's a couple of ways. So let me make things even simpler. Forget about where the electron is located and think about the electron is spinning, right?
Okay.
The electron is spinning just like the Earth spins. It's really exactly like that. It's like a little spinning top, except when you measure the spin, you can sort of send the electron through a magnetic field and it will get deflected either up or down, depending on whether it's spin up or spin down. You only ever get one of two answers. It's either going up or going down. It's nowhere in between. This is an empirical measured fact, okay? So that's a part of quantum mechanics. That's the quantum fact, that there's discrete set of possible answers to this question. Is it spinning clockwise or counterclockwise? Yes or no. It's just those two possibilities, nowhere in between. So if you have a magnetic field that is oriented vertically, send your electron through it, it gets deflected up, you say, oh, it's spin up. So now I've measured its spin. Now I know what its state is. If I send it through another magnetic field, or oriented vertically, it will always be deflected up every single time. We know what it is. We're going to measure it. Measuring it, in this case, doesn't change it. It's in exactly that state. We know it, okay? Now let's send it through a magnetic field that is oriented horizontally. So it's going to be deflected either right or left. We know exactly what state it's in. It's spinning this way. But when you send it through that magnetic field that's oriented horizontally, it gets deflected left or right 50-50, unpredictably. There's no way we can predict it. And then once it is, so okay, now it's been spinning up, you've measured its spin left, let's say, send it through another magnet that is going vertically. And now it's 50-50 again. It could be spin up or spin down. So somehow, even though we knew exactly what state it was in, we couldn't predict what would happen next. That is part of quantum mechanics.
So the act of sending it through these things where it makes it vertical or horizontal, what is happening to it when it's going through these things?
So in quantum mechanics, what we say is that it's not that we don't know whether the electron is spinning clockwise or counterclockwise. It can be in a superposition of both. That's just the spin version of the position of the electron can be spread out in a wave, right? It's truly not just that we are lacking some knowledge. It's that the knowledge really isn't there. And again, this is how we teach quantum mechanics in textbooks. And I'm going to correct it because Many Worlds is much better. But this is the standard textbook version. There's a wave function. The wave function for a spin is it's either up or down or some combination. And then there's a rule that says when you measure the spin, you only get up or down. You don't see the wave function. Just like the cloud that you have for the electron's position, when you look at it, you see it at a location. So another way to make the same argument is take a little piece of, I have a nice little image of this when I give talks, little piece of uranium. So it's a radioactive little chunk of metal, and you put it in a bubble chamber. So it is emitting radioactive particles, and you detect the particles. You can see a little streak of motion when the particle leaves the uranium, okay? Well, like I said, when you're not looking at it, this electron is supposed to obey an equation, the Schrödinger equation. And you can ask what the prediction is when a radioactive nucleus decays and gives off an electron, what is its wave function going to do? What is the wave function of the electron going to be? And the answer is, it goes off in a spherical wave. It goes off in all directions at once.
Evenly.
Yeah, all directions evenly. But you never see that.
Is
You
that roughly
always
based
see a
on the
line.
shape of the piece of uranium? Does it vary?
No, because the electron gets from one individual nucleus of an atom, right? So what the uranium is doing doesn't matter. It's just that one atom matters. And the easiest thing for the electron to do is just to go out in a sphere. It doesn't have to. It can go out in higher energy states. But the point is, it's not going out in a straight line. But when you look at it, you see a straight line, right? That's the fundamental mystery of quantum mechanics, that how we describe the thing when we're not looking at it is different than what we see when we look at it.
So when you're in pursuit of an understanding, a deeper understanding of quantum mechanics, when you're thinking about people from the 1900s that are just sort of basically getting the first steps going to understand this stuff, when you're talking about this lack of funding and the lack of encouragement for people to pursue quantum mechanics, you strongly feel like there are answers to these questions.
Yeah, that's right.
That we just need better tools and a better understanding, better equations, more time.
Yeah, me and Einstein think, right? So Einstein is one of the secret heroes of the book because he has this reputation